Okay, lesson 16, electric potential. All right, so a little bit of review on gravitational potential energy. We talked a bit about this last time too, but it'll be a good review here. So if we had some mass, right? So we have this thing. What was that I want? So we have this mass, right? Well, we've done this quite a lot. That if this is the Earth and I lift this thing up to point A, then I'm giving it gravitational potential energy, right? I'm giving it more energy. I'm doing work on the object to give it more potential energy, right? And so if I move the mass toward A, there's a gain in gravitational potential energy. If I move the object toward B, there's a loss, right? So if I move it back down, now there's going to be a loss in potential energy. And I don't know if you guys remember this, but if I move it in the direction of C, so perpendicular to the direction of the gravitational field, then I'm not changing the energy or the potential energy that it has, right? So yeah. So yeah, based on that idea, like I feel like we've done this a ton. We're going to do something really similar now with electric potential fields. So electric potential energy. All right, so same type of idea, but now remember electric fields can be attractive like gravity. Gravity is always attractive, right? That's all gravity does as far as we know. And electric fields, though, they can be repulsive or they can be attractive, and it depends on whether it's positive or negative, right? So in this case, if we had some charge, Q, some test charge, let's say, then this thing, right, if I move this toward point A, well, what's going to be happening is it's like a magnet, right? It's like having two north poles of a magnet pushing towards each other. It's like a spring even, right? I'm doing work to bring this thing over here, and it's getting harder and harder and harder to push. I'm giving it potential energy. But instead of gravitational potential energy like we had before when we lifted it up to A, we're giving it electric potential energy. So it's like it's a spring, and we're compressing that spring more and more and more and more, giving it that potential energy. And if I let it go, then it would quickly zip off towards that side, right? To back, like, away from the positive and toward the negative. So yeah, we're giving it the ability to do work. All right, so the same thing, if I move this object toward B, well, then I'm actually taking away, I'm making the energy less, or the change in energy less there. And just similar as before, if I move this thing in a path C, I'm not actually changing the potential energy at all. So yeah, very similar there. So electric potential energy is our new idea here, and it's the energy of a charged object due to its position in an electric field, right? So that's the definition of electric potential energy. Very similar to gravitational potential energy, right? It's the same idea. All right, electric potential. So if we have, let's say, some object Q, and we move it toward A, right? Then we're changing its energy. And really what we have there is this idea of a change in your difference in energy there actually has the name voltage, right? And it's going to be the electric potential difference. So you guys have probably seen that before with electricity, right? You've got your voltage, you've got your current, you've got your resistance, and we're going to do more of that as well. But really what your voltage is it's the change in electric potential is due to the change in the position of a charge within an electric field. So you give something more voltage if I move it from A to B. And that's really because you can think about it like it has farther to fall, right? If it started here and I bring it out to there now, then it's like it has a farther distance to drop, right? It's got more energy there. It's got more oomph, right? Like I was say, like our voltage is like the amount of oomph that it has, like pushing behind it, right? So the idea between voltage or potential difference, they mean the same thing, is this, right? Your voltage, so change in V, is going to be the voltage that you had at B minus the voltage that you had at A. And what we can actually say, like the formula for voltage is it's going to be the change in potential energy per unit of charge. All right, so it's not technically energy, it's energy per charge, right? So if you had like, let's say 1 electron, it's how much energy does this thing have for every one of those electrons. All right, so that's what voltage is. So voltage can be measured in joules per coulomb, right? Like energy per charge. And we've simplified that to volts, right? So yeah, so voltage is measured in volts. All right, so you guys can look through some of those questions. We'll move on to the next one though. So next part here is equipotential lines. And it's really similar to the same thing as above. So what the idea here is that if I've got a charged plate, right, like this one's positively charged on that end, and this plate is negatively charged on that end, then if I had some object A, right, some charge A, and then I move it to charge B, right, what's going to happen is I'm going to give it a difference in voltage, right? There's going to be a potential difference there. So the potential difference, if I move object A toward object B, would be exactly the same as the potential difference from moving charge C to charge B. And there actually is no difference in the potential, like there's no potential difference between A and C, right? So it only comes from the different, like there has to be like a drop, right? Like a difference in potential energy there. So one thing to notice on these ones, on these equipotential lines, is that if you start at one end of this plate, right? Notice that we got kind of a funny scale going on here. We've got 0 on one end, and you've got -20 on the same end. Well, what's going on there is that they're just kind of showing, like notice that this says or on this side, is that it doesn't matter where we call 0. You could actually call 0. We can make 0 right in the middle, or we can make 0 on one end. It doesn't actually matter. And that's just like your reference point, right? So this would be the same thing as if, you know, if I was on the earth or something, and remember how if I had like, you know, a person jumped up to here and they drop down, right? Well, I could make this point right here 0 energy or 0 joules, right? Or I could make it, you know, up here. That could be my 0 joules, right? We've talked about that before. So it's all relative to where you start. Okay. So it doesn't actually matter, right? So it's all about the difference in voltage, not where it starts. All right. Moving on. Okay, so I think for the most part here, we should be able to do some practice problems and be done. So we should be done pretty quick on this one, I think. So number 1, if 50 joules of work is required to move a 0.5 coulomb charge in an electric field, what is the potential difference between the 2 points? Okay, so this one's not too bad. So, oh, one thing though, guys, before we get going here, can you guys grab your form? If your formula sheets are close, it'd be good to grab. I need you to notice something about our formulas now. So things are going to change a little bit here. So this is kind of the area on your formula sheet that we're working in. And we have done, up until this point, we've done those, right? We've done those 3. And till now, if you can't find this, fine. Maybe just follow along with what I'm doing here. So we've done these 3, and till this point, these E's, right? That was our electric field strength, right? That was acceleration due to gravity. Like that's like our G, right? Like our lowercase g there. If you were talking about acceleration due to gravity. So yeah, what's changed here now is that this, right, is our new formula. This is energy, right? This is change in energy. So this would be like our EP or something like that. So it's kind of annoying that we have E for both of them, right? They're both E, but they have different, like they mean different things, right? Sorry, one sec, guys. My wife called me like 3 times there. I just gotta. Okay, I'm back, guys. Sorry about that. Okay, so yeah, sorry. Yeah, so anyway, like I said, these ones are going to be electric field strength. And this one's going to be energy. So just make sure not to get those confused, right? So if you can, mark it on your formula sheet just to make sure you're not going to make a mistake on that one. Let's go back here. All right, so we said, yeah, 50 joule work is required to move this many coulomb charge in electric field. What's the potential difference between the points? Okay, so we've got change in energy is equal to 50 joules. Charge is equal to 0.5 coulombs. And we're looking for voltage. And it really should be change in voltage, right? That's the only one that really matters. So this is just straight up putting in the formula. So your change in voltage is equal to change in energy over charge. So my change in energy was 50 joules. And my charge was 0.5 coulombs. So that's all going to be equal to a change in voltage of 100 volts. Okay, next one. So if an electron starting from rest falls through a potential difference of 500 volts, what is its final speed? All right, so on this one, what we're going to do, so let's write down what we know. So we know, so 500 volts, so we'll say change in voltage is equal to 500 volts. And charge is, okay, well, what would the charge be? I only really know the voltage right now, right? It does tell me, though, that it's an electron. So you guys should underline this or highlight it. You know, this is important. So electron, well, I know an electron has the elementary charge, right? And it's negative. So that would be a charge of 1.6 times 10 to the negative 19 coulombs. And technically, like I said, it's negative, but I'm not really going to care here when I get going. It's going to be, I'm going to be figuring out like a magnitude of this. I don't even know which way it's going. So it's not going to be too important, you know, what's happening like with the negative. So I'll put a negative there, but I'm going to drop it here in a second. It doesn't really matter. Okay. And then the mass. All right. So from your formula sheet, you got, or on your data sheet, you guys have this, right? So 9.11 times 10 to the negative 31 kilograms. Okay. So how does that help us? Well, let's think about what's happening here. We've got this electron, right? And it even says falls through a potential difference. So it's like it's got like a bunch of energy over here, right? It's got a bunch of energy and it's falling this way, right? And then all of that energy it had to begin with turns into, well, in the end, it's all going to turn into EK, right? It's going to turn into speed. It's all based on how fast it's going in the end. We've done this before, right? Remember how we had like, okay, at the beginning, we had potential energy and all of that potential energy ends up turning into kinetic energy. Well, before it was gravity usually, right? We'd lift something up and it would turn into kinetic energy when it fell. We got the same thing. So we're going to start this off by saying EP is equal to EK, right? All of this EP is going to turn into this EK. But now the EP is the only thing that's changed. We just have a new formula for EP now. So EP is going to be charge times voltage, charge times change in voltage. So I'm just replacing EP with that, right? And that's equal to, and then EK is equal to 1/2 mv squared, which is perfect because they're looking for velocity, right? So now we just need to solve for V. So just for the sake of time here, I think you guys are pretty good at this now. Are you good if I just rearrange this to be 2qv over m, and then take the square root would be my V, right? Just rearranging everything there. So that would be equal to 2 times my charge of 1.6 times 10 to the negative 19 coulombs times 500 volts divided by my mass of 9.11 times 10 to the negative 31 kilograms. And then take the square root of all of that, and we get 1.33 times 10 to the 7 meters per second. So extremely fast, right? Like that's actually, if you think about that, that's quite impressive. Especially if you think about it, like the speed of light is 3 times 10 to the 8, right? This is 1.33 times 10 to the 7. So this is like, we're kind of getting to be like a fraction of the speed of light when you're getting going that fast, right? Okay, last one. So now it says a completely ionized aluminum nucleus. So ionized. You might not know what that is. You might from chemistry. If you don't, that's fine. What ionizing means is to completely strip all of the electrons off of the atom. So on an atom, right, you've got protons are in the nucleus, protons and neutrons, and you have electrons that are going around the outside, right? Well, if an atom is ionized, what that means is all the electrons are gone. All right, so that's what that means. And it's accelerated through 0.25 megavolts potential difference. What's the final speed? Okay, so this one's not too bad if we know a couple of things here. So if it's completely ionized, what I want to do is I want to go to our, and this will be the first time that you guys are going to need to look at your periodic table, which seems weird in physics, I know. So I've got my periodic table. I'm looking at aluminum, right? And just as a little bit of chemistry review, the atomic number there, that 13, what that means again, right? That means that you've got 13 protons and 13 neutrons. Well, we've just been told that this thing has been completely stripped of all of its electrons. So the question is, how many extra protons would there be then, right? Like what would the charge of this thing be? Well, it's going to be 13 elementary charges, right? It's going to be 13 of those 1 times or 1.6 times 10 to the negative 19s, right? That elementary charge. And it'll be positive because it's missing all of its electrons. Okay, so that's the case. The other one here, let's just remember this one so I don't have to come back. The atomic mass. So remember the atomic mass on the periodic table is really your protons plus your neutrons, right? That's them together. And sometimes you'll have like, maybe 1 or 2 more neutrons, but the idea is that would be all of your protons and neutrons together. So we'll just remember those 2 numbers and go back to our question here. All right, so what we can say is that the charge that we're actually dealing with on this thing the charge would be 13, right? The atomic number, because that's how many protons we have, right? And then that times positive 1.6 times 10 to the negative 19 coulombs. Okay, so our charge is going to be 2.088 times 10 to the negative 18 coulombs. All right, and our voltage here is going to be, let's just write this a little different than megavolts, will be 0.25. And then the mega, you can just replace with times 10 to the power of 6, and then volts. All right, and then the last one here, we'll do the mass, right? We want to figure out what the mass of this guy is. So the mass, remember the atomic mass on the last page was, what was that, like 26.98? What we would do is round that up to 27, right? So there's 27 protons and 27 neutrons in the nucleus here. And that's all there is because the electrons are gone. So that'd be 27 times the atomic mass, right? So that's going to be 1.67 times 10 to the negative 27 kilograms. All right. This is on your data sheet too. And I just want you to know this, that it's actually the same mass for a proton and a neutron. They're very, very similar. Like in the unit coming up, we're going to talk about how they are slightly different, but they're for our extensive purposes, they're very close. So we can just assume that they're all the same mass, protons and neutrons. And then that will be equal to 4.509 times 10 to the negative 26 kilograms. Okay, and then we have everything we need. So we can do this again. We can say, okay, energy before, so potential energy is equal to kinetic energy, right? So this thing had a certain amount of potential energy to begin with. Our new formula is charge times voltage. And our kinetic energy is the same thing it's always been, 1/2 mv squared. Okay, and then rearranging the same as last time. We'll just do it the same way, right? V was equal to the square root of 2qv over m. So that would just be 2 times 2.08 times 10 to the negative 18 coulombs times 2.5 times 10. Oh, either way, you can write this let's write it the other way just so that we don't confuse ourselves. It's just the way it is on my sheet, but I'll write it the same way as it was up here. 0.25 times 10 to the 6 volts, which would be the same thing as 2.5 times 10 to the 5 is what I was going to write, over 4.509 times 10 to the negative 26 kilograms. And then that was all square root. So in the end here, we get a velocity of 4.8 times 10 to the 6 meters per second. Oh, yeah. So quite a lot slower, actually, right? Which kind of makes sense because this is a proton now instead of electron. It's a lot more massive than the electron was. So I'd expect this thing to be going slower than the electron would. So, okay, so that's it. Just one sec.